Okay, guys, so today we're going to actually be reviewing two topics we already learned and then adding in the information for quadratics. This is going to be dealing with models. We're going to be looking at graphs and seeing what they look like every time when they're each one of these three models. We're also going to be looking at the patterns that are created in tables when you see these types. So we're going to take a look at these and see what each one of them is like. By the end, you're going to need to be able to identify whether each one of these models is linear, quadratic, or exponential. Hopefully it'll be pretty straightforward. This is one of the sections that people usually like, and it's kind of a buffer on this one. People tend to like this one. So let's get going. So there are going to be three types of functions we're going to be talking about today. We're going to be dealing with linear, which is that y equals mx plus b. You've seen that many times. You get a graph that makes a line. It can go in any direction. This one happens to go up and to the right, so it's got a positive slope. But this is the representation on a picture of a linear model. For the next one, it's quadratic. This is everything that we've had so far on quadratics, where you see the ax squared plus bx plus c. We've just spent this entire chapter working on quadratics and factoring and solving those quadratic equations. When you look at a graph of it, it makes a parabola. This parabola is going to go up or down. Okay, it can be happy, they call it, if it faces up, or be sad when it faces down. And so this is the model of a quadratic. Okay, the last one, this model right here, is exponential. We've done these before. That's that y equals a times b to the x. You're going to see it's going to go up and to the right. It can go down and to the right. You can go the other way down here and to the left, or up and to the left. There are 4 different ways that you can show exponential, but this is what the picture of it looks like. It will not have another side of the curve like a quadratic does. It goes and does both sides. This has just one steep hill or one deep valley if you're going down. Okay, so let's take a look at our problems. You're going to graph these points and then decide which model is the most appropriate for each set. So when you take a look at this, you're going to see that you've got these points, 1, 3. When we graph points, don't forget you go left or right first, then up or down. So 1, 3 would be to the right 1 and up 3. The next one is going to be 0, 0, so it's right on the origin. The next one is negative 3, so to the left 3, and then positive 3, so we go up 3. The next one is going to be negative 1, so to the left 1, then down 1. And then finally negative 2 and 0. That means go to the left 2 and then don't go up or down. As you can see, this is going to be modeling something that has 2 identical sides. When it looks like this, we're going to be looking at what type of model that looks like this. That is a quadratic. That is correct. So quadratic is the model that's represented here. Okay, for our next one, we have 0, 2. 0 means don't go left or right, go up to 2, put a point. The next one is negative 1, 4, so go to the left 1 and then up positive 4. For the next one, it's 1, 1, so you start at the origin, go to the right 1 and up 1. And then 2.5, so over 2 and then up half of a point. Oh, we're making a curve right here. So we're going to see that curve, and it goes up very strong. You've seen this curve being shown a lot with the new virus that's going around. It's growing exponentially. It goes the other direction, goes up and to the right, but it is still an exponential curve. And so because of that, this is an exponential model. Okay, guys, so the last one has these points right here. Let's graph these. Negative 1, negative 2 means go to the left 1 and down 2. 0, negative 1 means don't go left or right, go down 1. 1, 0 means go to the right 1 and then don't go up or down. And 3, 2 means go over to 3 and go up 2. And you'll see that all of your points are in a straight line. We can draw our line through here and sketch it. You know I'm not very good at these, but there you go. So that means if it makes a straight line, this is representing a linear model. And that's what you need to be able to do, is identify those different models. Okay, so the next type of problem we're going to be doing is doing the same process but doing it from a table. So let's show you what that looks like. We've done this already for linear and exponential. The only one that's new is the quadratic. So let's show you how to find that. So getting started, we'll take a look at these. Don't forget, every single time you do this, you're going to be asked to go through and find the difference and the change on each side. So you need to go through and find that difference. So what is it doing from -2 to -1? It is increasing by 1. From -1 to 0, it's increasing by 1. And from 0 to 1, it's increasing by 1. On this side, it is going to be increasing, but it's going to be increasing by 3. From 2 to 5, increasing by 3. 5 to 8, increasing by 3. Since it is constant over here, it is the same every single time, and you're adding the same every time. This is going to be called a constant rate of change. The other term for that is just slope, guys. And whenever you have a linear, it's going to be adding that same thing every single time over on this right-hand side. Okay. So if we look at the next model, the exponential, again, we've already done this one, but let's keep going. Just remind you of what you do every single time over here. You're adding 1 every single time. What we do on this side is what we've got to figure out. Well, it's getting bigger, but it's getting bigger by different amounts. But if you multiply by it every time, you'd get the same thing. If you multiply by 2 here, and then multiply that by 2, and then multiply that by 2, you'd get the same thing every time. There you go. So if you multiply by the same thing every time, it is called a constant ratio. And that constant ratio means that you're going to be dealing and looking at that exponential. Remember, if you add the same number every time, it's linear. If you multiply by the same number every time, then it's going to be exponential. Now we need to look at quadratic. This is the one that's new. So for this one, we're still doing +1 every time out here on all of these. That's constant on this side. What we're looking at is what happens over here. So when we look over here, there are different amounts every time. So we're not adding the same thing. We'd add 2 here, 2 here, 5 here, 10 here. That won't work. We wouldn't multiply by the same thing because this one's positive and then negative, then positive again. That won't work. So let's just see how much you'd have to add every time. Well, to go from here to here, you'd be subtracting 2 to go from there to there. And then from -1 to 1, you'd be adding 2. And then from 1 to 7, you'd be adding 6. And then from 7 to 17, you'd be adding 10. Well, none of that fits either of these two models. So now we have to do something different. Well, you basically have to do another level. You go out here to the side, and if none of them are the same, then you do it again. From -2 to 2, you would be adding 4. From 2 to 6, you would be adding 4. And from 6 to 10, you'd be adding 4. And if you add the same number every time on that second level, then you're looking at a quadratic model. So let's write that down. If you add the same number on second level, that's when it's going to be that quadratic model. Okay, adding the same number on the second level. If the first level doesn't add the same or multiply by the same, then look at that second level. Okay, let's do the next one. Here we go. Okay, so we look at the change on this side. Every single time it's adding 1, every single time, so it's going to have that constant on the x side. Now we need to look at what it's doing on this right side. It's definitely not adding the same thing every time, so let's see if we can multiply by the same thing every time. If I multiply by 2 every time, does it give me the same thing? Yes, that works. If I multiply by the same thing every time, that's going to be that constant ratio, which means it is going to be exponential. There you go. it's going to be an exponential model. Okay, for the next one, we look at the first one and see if it's the same every time, which it is. It's +1 everything on this side. So we look at this side over here, and we look to see what it's doing every time. Are we adding the same thing? Are we not? Are we multiplying by the same thing? Are we not? And we see what it is that's happening every time. For this one, we are, interesting. We are subtracting by 0.25. No? These are all different. Let's see then if we do this and we go through how much we're changing. We can't multiply by the same thing every time. We can't add or subtract the same thing every time. So let's just see what happens every time. This is minus 0.25. This one would be minus 0.75. This one would be minus 1.25. And this one would be minus 1.75. So none of those are the same. They're not doing the same thing every time. So whenever we have that, we look at that second level. Between here and here, you would be minusing 0.5. Between here and here, you would be minusing 0.5. And between here and here, you would subtract 0.5. Because of that, the second level is the same every time. That means it's going to be quadratic. Okay, now look at the next one. It's the same over here. Every single time you are adding 1, all the way down. Then because of that, we look over here to see what happens. It's decreasing every time. Let's see if it's decreasing the same. -4, -4, -4, -4. It is subtracting by the same amount every time. So with the one that works with adding or subtracting the same number, that constant rate of change, that's going to make it a linear function. Okay, guys, that's the last of our examples today. If you have any questions, remember you can attend the help session, and I'll see you next time.